Good morning, sir.
Good morning, Professor Mera.
I hope you are doing good, sir.
Yep. Can you see my slide?
Yes, sir, it's visible.
Okay, how about this?
Yeah, sir. Yeah, it's okay.
Okay.
Good morning, everyone. On behalf of Professor Shinji Tokunami sir, our esteemed foreign coordinator, and Dr. Rohit Mehra sir, Professor at Dr. B.R. Ambedkar National Institute of Technology, I extend a warm welcome to all the participants on the fourth day of the GIAN course. Further, without further delay, I now invite Professor Shinji Tokunami sir to commence the first lecture of today's session on radon and thoron. Tokunami sir, are you there?
Yes, can you hear me?
Okay, sir. You may continue your lecture.
Okay, thank you.
Okay.
Thank you for your kind introduction. So yesterday I explained the radon surveys in various countries, but today, at the beginning of this lecture, I will focus on Toron issues. Actually, this Toron issue is site-specific, especially in Asia. As you can see, Toron is often neglected in indoor environment because of its short half-life. Look at this. This is Toron radon 220 with 56 seconds of half-life. Due to its short half-life, Toron cannot travel far from its source. Its inhomogeneity of Toron concentrations in the environment. As you know, knowledge and research on Toron are limited compared to radon research, not specifically covered in recommendations or regulations. In addition, no standardized measurement method is currently available. In the Toron study, we have to take into account polonium-216, lead-212, bismuth-212, and polonium-212 for those assessments. Toron can still be hazardous due to its progeny, including lead-212, the half-life of 10.64 hours, which can accumulate to significant levels in breathable air. Recent studies indicate that in some regions, the dose due to Toron and its progeny can be higher than that of radon and its progeny. Therefore, the global interest in Toron exposure is increasing. Toron interference can be regarded as one of the major uncertainties of radon measurement in indoor radon studies. Consequently, some studies are focused on developing discriminative systems to enable the distinct measurement of these isotopes. Here is our detector, Radioactivity, in cooperation with a Hungarian company. Here is an Indian detector, LR115 detector is used as a detecting material. Both of two detectors, they have same principle for discriminating two radon isotopes by using difference of half-life, their half-lives. In the Indian detector, there is a pinhole. Just only here is a radon and tolon gas. Radon and tolon gas only can enter inside, and radon and tolon gas are filled with this chamber. In the chamber, then the gas goes through the pinhole. Therefore, only radon gas can go through this pinhole due to long half-life of radon. Here there are two methods, two ways for those assessment of tolon and tolon progeny. In direct method, this is the same as radon. Measure the tolon concentration. According to unscaled report, they provided a typical equilibrium factor of 0.02, but I don't believe this is reliable. Then, anyway, after using the typical equilibrium factor, we can calculate equilibrium equivalent tolon concentration. Multiplying exposure period, we get the time integrated equilibrium equivalent tolon concentrations in becquerel hour per cubic meter. After that, using dose conversion factor, finally, we will get the effective dose. On the other hand, we can propose a direct method. As you might know, we can estimate tolon progeny concentration directly. So we use the direct value of EETC, equilibrium equivalent tolon concentration. Then finally, we get the effective dose. Dose assessment of tolon with direct method, equilibrium equivalent tolon concentration is expressed like this formula. D is the track density, tracks per square millimeter. C is a calculation factor, conversion factor. In our tolon progeny monitor, only polonium-218 alpha particles can be detected with the thick energy absorber, because polonium-2 energy is the highest, higher than other radon progeny. Only this energy can be detected with CR39, solid-state nuclear track detector. Based on this principle, we get the conversion factor here, like this. And T is exposure period. This is a passive technique for tolon progeny measurement. In our detector, the lowest detection limit of the equilibrium equivalent tolon concentration is estimated to be 0.005 becquerel per cubic meter with a 90-day exposure. I will show you some result of tolon surveys in Cameroon. The arithmetic mean of E equilibrium equivalent total concentration was approximately 22 times higher than the world average value of 0.5 becquerel per cubic meter. This table summarizes a result of Toron survey, Toron and Toron progeny survey. 130 houses are covered in this survey. This figure shows the frequency distribution of Toron concentration indoors. Radon concentration in this survey is 103 becquerel per cubic meter at the arithmetic mean. Toron concentration was 173 becquerel per cubic meter. Equilibrium equivalent radon concentration was estimated to be 41 becquerel per cubic meter. Equilibrium equivalent Toron concentration was 10.7 becquerel per cubic meter. The contribution of Toron to inhalation dose due to radon and Toron exposure ranged between 12 to 67, 3 to 80, 7 to 70, and 7 to 60% in the north, south, east, and littoral regions respectively. From this survey, these findings emphasize the critical need to include Toron in the inhalation dose assessment for radon exposure. In Canada, simultaneous measurement of radon and Toron were conducted in a total of 3,534 residential homes across 34 metropolitan areas. Indoor radon and Toron concentrations are not correlated, and Toron concentrations cannot be predicted based on widely available radon data. Here is a result of the survey in Canada. On average, Toron contributes 4% of the radiation dose due to total indoor radon exposure. Regarding geographical locations of high background radiation areas, most of we have major high background areas in Asia. Yanjiang in Guangdong province, China. Takandiam, Mamuju in Indonesia. Karunagapalli in Kerala, India. In China, Yanjiang, Guangdong province is famous for being one of the areas with the highest background radiation in the world. The Toron concentration was approximately 10 times as high as that of radon. Look at this. This is a summary of the survey. Radon concentration is 124 becquerel per cubic meter at the arithmetic mean. Toron concentration is 1,247 becquerel per cubic meter as the arithmetic mean. Equilibrium equivalent Toron concentrations was 7.8 be글박입니다. Using these data, we calculated the annual effective dose. The annual effective doses due to radon and thoron progenies were estimated to be 3.1 plus minus 2.0 millisievert and 2.2 plus minus 2.5 millisievert respectively. The radon dose was comparable with the thoron dose in this area. Here's the frequency distribution of the total dose in China, in Yanjian area. In Kerala, India, the geometric mean of inhalation dose was evaluated as 0.10, 0.44, and 0.54 millisievert for radon, thoron, and both of them respectively. This table shows the summary result of the survey conducted by our research group. High background radiation area and control area. Here's the number of house, the mean value, median value, and range. As you can see, the radon concentration indoors is comparable to that outdoor concentration. But in terms of thoron and progeny, a little bit higher than other countries. Therefore, the internal dose from thoron progeny was found to be more significant than that from radon. This figure shows the effective dose from radon and thoron exposures. Here's the number of doings. As our data analysis, there was no correlation between radon and thoron concentrations or between thoron and thoron progeny concentrations. Then we can say exposure to thoron cannot be predicted from radon exposure. Equilibrium equivalent thoron concentration estimation from thoron concentration involves significant uncertainty. Here's the relationship between thoron concentration and radon concentration. In this figure, the relationship between thoron concentration and thoron progeny concentration, namely equilibrium equivalent thoron concentration. Regarding Indonesia, Mammoth is recognized for having a radiation dose rate approximately 13 times higher than the normal level. In Takandian, the concentrations were consistent in both indoor and outdoor areas, including thoron in dose assessment is crucial. This table summarizes the result of the survey conducted by our research group. Radon, indoor, outdoor, thoron, indoor, outdoor, and equilibrium equivalent thoron concentrations, indoors and outdoors. The radon concentration indoor radon concentration ranged from 42 to 900 becquerel per cubic meter. Surprisingly, outdoor radon concentration ranges also from 49 to 435 becquerel per cubic meter. So we calculated the annual effective dose based on the activity concentration of each radionuclide. Radon gave 3.4 to 12.1 millisievert. In the case of thorium, 5.1 to 17.7. As a total, annual effective dose was estimated to be 9.8 to 28.6. The arithmetic mean of annual effective dose, total annual effective dose, was estimated to be 18.2 millisievert per year. In Ireland, Europe, the first nationwide assessment in Europe of annual effective doses from both radon and thorium. Between 2007 and 2009, long-term indoor concentration of radon gas and its airborne progeny were measured in 205 dwellings across Ireland. In 14 of these dwellings, the estimated annual dose from thorium progeny was higher than that from radon. Here is a summary of the survey. Regarding thorium concentration, arithmetic mean 22 becquerel per cubic meter, the maximum value 174 becquerel per cubic meter. Thorium decay product concentration as equivalent thorium concentration, arithmetic mean 0.47, the maximum value 3.8 becquerel per cubic meter. So we estimate annual effective doses from thorium decay products, arithmetic mean 0.35 millisievert per year, the maximum 2.9 millisievert per year. In Japan, the first national survey was conducted using a Karlsruhe type radon monitor. Here is a sectional view of Karlsruhe type radon monitor. As I explained previously, the arithmetic mean radon concentration recorded was 20.8 becquerel per cubic meter. This monitor has had a relative thorium sensitivity of 78% compared to radon sensitivity. Data are not suitable for estimating the national effective dose. So we revealed in this first survey, we revealed thorium interference in the radon measurement with this monitor. Therefore, we conducted another survey. The second national survey was conducted using radon-thorium discriminating monitors. The arithmetic mean radon concentration was 15.5 becquerel per cubic meter, approximately 5 becquerel per cubic meter, lower than that of first survey. Also, recently we conducted a small regional survey in Fukushima. Here's a frequency distribution of indoor radon concentration. The number of houses. The right figure shows the frequency of indoor tone concentration. Here's a summary of with a table. Radon, mean radon concentration was 48 becquerel per cubic meter. The radon concentration ranged from 16 to 242 becquerel per cubic meter. In terms of tone, the mean value is 59 becquerel per cubic meter. It ranged from 34 to 97 becquerel per cubic meter. Also, we conducted radon tone surveys in Thailand, especially Chiang Mai province. As you might know, Chiang Mai is the highest lethal lung cancer mortality rate. Data were collected from 44 dwellings in between March and May 2020. Radon provided a greater annual effective dose to the residents than tolon. Although Chiang Mai is the highest lung cancer incidence place, but radon concentration is not so high in this survey. The mean value of radon about 60 becquerel per cubic meter. The tolon is lower than radon, 19 becquerel per cubic meter. But here is a equivalent radon concentration and equivalent tolon concentration. Here's a summary of National Survey of Radon Isotopes. Radon exposure is subject to regulation. National Surveys provides essential data on the distribution of radon and tolon concentrations across different regions and populations. Survey results highlight regional variations with some areas exhibiting higher radon and tolon levels due to geological and environmental factors. Continued monitoring and research are essential for refining risk assessment and improving public health interventions. Collaboration between government agencies, researchers, and public health organizations is crucial for addressing radon and tolon-related risk effectively. This is the end of this lecture 6. Dr. Mera, I can receive some questions from audience.
Thank you very much, sir. So in case participants have any question, please unmute yourself and you may ask the question. Dear participants, if you have any question, then you may ask by unmuting yourself. So in case participants do not have any question, we can continue with your lecture, sir.
Yep. May I start again?
Yes, sir. You can start again, sir.
Okay. So I'm moving on the lecture 7, quality assurance and quality control for radon isotopes. Here are key messages from WHO handbook. Radon measurement in homes are easy to perform, but need to be based on standardized protocols to ensure accurate and consistent measurements. Long-term integrated radon measurements are preferred for assessing the annual average radon concentration within the house or other dwelling. High temporal variation of indoor radon makes short-term measurements unreliable for most applications. The type of detector should be carefully selected since it influences the cost of measurement per dwelling and therefore the cost of a radon program on a national level. Quality assurance and quality control measures are strongly recommended to assure the reliability of radon measurements. Quality assurance means the set of planned and systematic actions put in place at specified stages of the radon measurement process to ensure confidence and accuracy of the measurement results. Quality control means the quality checks carried out within the radon measurement laboratory as part of the overall quality assurance system. Therefore, quality assurance and quality control measures are strongly recommended to assure the reliability of radon measurements. Quality assurance is a broad concept that includes all matters that individually or collectively influence the quality of measurement. Implementation of quality assurance standards and guidelines to ensure confidence in the measurement results is strongly recommended. All entities, such as individuals, businesses, government agencies, etc., providing measurement services, should establish and maintain quality assurance programs. Regarding quality assurance plan, at the heart of a quality assurance program is a quality assurance plan, which includes written standard operating procedures, written procedures for attaining quality assurance objectives, and a system for recording and monitoring the result of quality control measurements. Minimum detectable concentration. Any entity performing radon measurements should calculate and include the minimum detectable concentration for its measurement system in its quality assurance plan and report it with the radon measurement results. For calibration of detectors, individual for an active monitor or batch of passive detectors should be prepared. Detectors are exposed to the standard atmosphere under known conditions to get a calibration factor. That is a factor that converts the detector response to its true value. The detector is calibrated as received by the calibration laboratory. However, if any part of the detector that may influence the response to radon, that is a measured entity, such as a new batch of solid-state nuclear track detectors foils or a new readout microscope is used, the calibration should be updated. Use the detector under calibrated settings, high humidity, high attach fraction ratio to avoid measurement uncertainties. Calibration should be conducted annually or semi-annually, depending on the manufacturer's suggestion and licensing and certification agency requirements. So I'll show you the example of the calibration. Time variation of radon concentration in the radon chamber during the exposure test is observed using active radon monitors. Radon monitor was measured by AlphaGuard, which was calibrated by PTB, Germany. This figure exemplifies time variation of radon concentration. This is a photo of AlphaGuard. This is old type and new type. In our case, radon concentration, temperature, and relative humidity in the radon chamber vary over time during an exposure test. Radon concentration was measured using a pulse-type ionization chamber, namely AlphaGuard, calibrated by PTB as well. This figure shows the time variation of radon concentration, temperature, and relative humidity in the radon chamber. Here is a radon concentration and relative humidity, and this is a temperature. Using this facility, we can achieve the calibration for passive radon monitor. Here is the relationship between the time-integrated radon concentration and track density after exposure. Normally, in our case, we set 3 different exposure levels to obtain the linear relationship. Statement of certificate of calibration is then issued containing the following information. that is, the condition of the monitor as received, including any physical damage and settings of discriminator, voltage, background, and calibration factor as necessary. The measured background, the measured response to the reference atmosphere, the settings of discriminator, voltage, background, and calibration factor as calibrated, the date the calibration was performed, and the name and signature of the person responsible for the calibration. The level is labeled with a sticker saying that this device has been calibrated, the expiry date of the calibration, and the calibration factor. Background measurement. In terms of reactive monitors, over time, the atoms of lead-2 and 210 accumulate in the detector. And then the activity of alpha-emitting polonium-210 increases, and the background of the detector increases. Repeated measurement of detector background every half year or in shorter time periods if necessary. The measurement of the detector background should be recorded. Passive detectors, laboratory background measurements. The inherent background of laboratory equipment, which is used to analyze the detectors, must be measured and subtracted from the response of detectors used in the field. Background measurements are also used in establishing of detection limit and minimum detectable concentration. Field background measurement. Field blanks, detectors which are handled in the same manner as those for field measurement, but are not exposed to the ambient atmosphere or are stored in the low radon atmosphere. In terms of intercomparison exercises, as far as possible, entities performing radon measurements should be participate periodically in inter-laboratory comparison exercises. Such exercises are typically carried out in one of two ways. First one, a continuous radon monitor may be chosen as a transfer standard and sent to several reference laboratories for exposure in systems for test atmospheres with radon, namely STAR. This was used in IEC standard. Once the continuous radon monitor has been received at the laboratory, the operator of each STAR compares the values generated by the transfer standard with the values generated by the system that is used to monitor the STAR. This method can only be used between facilities that have STAR. Radon measurement from STAR must be traceable to the primary national reference standard by an acceptable intercomparisons method. Second, the other method requires a radon reference facility that has a STAR to host the exercise. Entities that perform radon measurements then send devices to that facility for exposure in the star. The devices are returned, but the concentration of radon to which they were subjected is not disclosed. Each entity then reports its results to the host facility, which then issues a report comparing all the participant results with the conventionally true values. As part of the intercomparison exercises, cross-checks for detector sensitivity to toron should be considered. Usually, the measurement is carried out at different radon levels, different relative humidity, and aerosol spectra, such as size distribution and unattached fraction. Dr. Mera, may I have a short break?
Yes, sir, definitely, sir. So,
Yep.
so we are taking a break of now 15 minutes, and we will be, dear participants, we will be resuming the session at 11 a.m. after 15 minutes.
Hello, Tokonami sir, are you there?
Yes, I'm here. Can you hear me?
Yes, sir, I can hear you, sir.
Okay. Can I resume?
Can we start, sir?
Okay, I do it. Okay. So I would like to introduce radon and tron reference chambers at our institute, Hirosaki University, Japan. Here is the outline of our radon exposure system. The system consists of 4 parts. Radon generation unit, mixing chamber, is an inner volume with 150 liters made of stainless steel, and monitoring unit. In this unit, radon concentration, temperature, and relative humidity are measured. Here is the exposure chamber. The value inner volume is 540 liters. This is our environmental monitor. Here is alpha gun to measure the radon concentration. Radon concentration is continuously measured by calibrated alpha gun. As I told you, environmental parameters are continuously measured by an environmental monitor. Regarding exposure chamber, this figure shows time variation of radon concentration at different exposure levels. Here I show you 5 levels. The lowest is about 300 becquerel per cubic meter. The low level 1,500 becquerel per cubic meter. Medium level 4,000 becquerel per cubic meter. 5,000 becquerel per cubic meter. The highest more than 10,000 becquerel per cubic meter of radon. As you can see, we keep the constant radon concentration in the exposure chamber. Here is a photo exposure chamber. Acrylic chambers of 540 liters is used for radon exposure. We confirmed the homogeneity of radon concentration in the exposure chamber. This figure shows an example of continuous measurement in a radon exposure chamber. Continuous measurement is possible under different radon concentration levels. The first case, radon concentration of around 800 becquerel per cubic meter. Then we change the radon concentration up to about 3,000 becquerel per cubic meter, like this. Also, we can measure the radon progeny concentrations such as equilibrium equivalent radon concentrations. And also we took air samples intermittently to check the reliability of the data. Here, this is a square dot ERC from graph sampling method. This is polonium-218 concentrations. There's a good agreement between continuous monitor and graph sampling method. Here's an example of alpha energy spectrum and particle size distribution in the exposure chamber. During 0 to 1300 minutes radon concentration, about 800 becquerel per cubic, we obtained the alpha spectra like this. Polonium-218 and polonium-214. Regarding particle size distribution, count median diameter, it was 69 nanometer, and the geometric standard deviation was 1.9. After changing the radon levels, radon concentration went up to 3000 becquerel per cubic. Here's the alpha energy spectrum of radon progeny, the same as above. Regarding particle size is almost the same. Then I'll show you the outline of Toron exposure system. The system mainly consists of 4 parts. Toron generation unit, monitoring unit are the same as radon. Exposure chamber. In the previous, in the radon exercise, we use this chamber as a mixing chamber. But for Toron calibration, we need a smaller volume to get the homogeneity of Toron concentration in the chamber. Toron concentration is measured by Radon 7. This device is based on electrostatic correction method. We are using lantern mantles as a Toron source because this mantle contains relatively high thorium-232. Toron concentration obtained from Radon 7 is corrected by the conversion factor value with scintillation cell technique. In details, for Toron generation system, open air go in through this filter and by pump. Then air was dried, this diffusion dryer, and goes through the flow meter and divided into 2 routes. The first one, this air goes through the humidifier. The other one is only just dry air, go this way. Then air, mixed air, penetrate through this Toron source and go to the chamber, exposure chamber. Toron concentration depends on the humidity in the toron source container. The humidity is controlled using different flow rates of X liters per minute and Y liters per minute directions. Total flow rate is set at 10 liters per minute. This figure exemplifies the time variation of toron concentration. By changing the flow rate, we can set at different toron exposure level, like this. Relative humidity 10% is the green dot. 40%, the maximum highest concentration is provided with high humidity, 60%. Therefore, toron concentration can be controlled between 3,500 and 30,000 becquerel per cubic meter. Here is the outline of radon and toron progeny chamber, aerosol chamber. The system consists of 5 parts: radon toron generator, aerosol generation unit, mixing chamber, monitoring unit, the same, and exposure chamber. In our aerosol generation unit, we use the aerosol generator model 3076 TSI company in the United States. Here is the relationship between flow rate of the aerosol generator and average number concentration. As the flow rate increases, the aerosol number concentration will increase. Also, here is aerosol particles are generated using sodium chloride solution, model 3079, with 1000 ppm, model 3076, the 500 ppm of sodium chloride solution. Aerosol concentration can be controlled between 800 and 230,000 particles per cubic centimeter by changing the flow rate of aerosol generator. Same. This device is a scanning mobility particle sizer, which measures a particle size distribution. The TSI company as well. This figure exemplifies a particle size distribution of aerosol, sodium chloride aerosols. With 1000 ppm, the median diameter was estimated to be 60 nanometers. But in the case of 50,000 ppm sodium chloride solution, the median diameter was estimated to be 113 nanometer. Aerosol size can be controlled between 60 and 110 nanometers by changing the sodium chloride concentration of solution. As you see here. Here's this concentration of sodium chloride solution in ppm. And this is a median, aerosol median diameter. This figure shows a time variation of particle size distribution with sodium chloride solutions. That's 10 ppm with 4 liters per minute. The particle size becomes stable at about 55 nanometers. In the case of 1000 ppm, particle size became stable at 70 nanometers. And in the case of 10,000 ppm, this is not so stable compared to a lower concentration. We also checked a different solution with potassium chloride. So you can see 100 ppm, stable at about 55. 1000 ppm, stable at about 80 ppm, 80 nanometers. If we took a higher concentration, the performance was not stable. Regarding exposure chamber, aerosol number concentration can be stabilized in exposure chamber. Here, the number concentration, you can see the concentration is stable, constant. Equilibrium factor, equilibrium equivalent radon concentration can be stabilized. Where are the intercomparisons organized? Here are examples of laboratories providing intercomparison measurements. I will show you 5 reference laboratories. The target of instrument in the UK, passive only, with radon atmosphere can be available. Every year, PHE organized intercomparison exercise. BFS Germany is also just for passive instrument. Radon atmosphere available. They organized intercomparison every year. Korea, this is India, Mangalore University, instruments, target instruments of active and passive. Radon atmosphere available upon request. Thorough check active, passive, and atmosphere radon and thorium upon request. our institute, we can offer the active and passive instrument test with both radon and thorium atmospheres. Upon the request, we can make intercomparison upon request. Here's an example intercomparison exercise. From the applied radiation isotopes, international intercomparison. Our paper was published in 2009. International intercomparison of integrating passive detectors in the nearest radon chamber. So I show you the international intercomparison experiment of passive radon thorium detectors in NIRS chambers in 2010. The case of radon chamber, the number of participants increased year by year. And also we have some experiences on intercomparison exercise for thorium detectors. This table shows the participant list of type of detectors. Many countries participated in our intercomparison. Poland, Czech, Romania, Sweden, Thailand, Hungary, Ireland, Korea, China, Italy, Ukraine. So we set at least 3 different exposure levels. Low exposure, that means average radon concentration is about 1,000 becquerel per cubic meter. The medium, this is not, we set different exposure level by, we control the time. The radon level is 1,000 or 10,000 becquerel per cubic meter. The time variation of radon concentrations is in our radon chamber. The radon concentration in the chamber is monitored by alpha guard calculated at PTB, Germany. In this exposure test, we also monitored temperature and humidity. In this case, the average temperature is 21 degrees and relative humidity is 57%. These environmental conditions need to be realistic in an actual environment. In our exercise, 70 of results were in a good agreement with a reference value of radon concentration in the chamber. This is a reference value. This figure shows the detector results with measurement uncertainty of radon exposure for all detectors during all experiments with percentage deviation of 20% from the reference value of the concentration. Reference value was given by our alpha guard calculated at PTB. 70% of result in a good agreement. Intercomparison exercise in field. Detectors, passive or active, are usually used in field, not under standard laboratory conditions. Intercomparison under field conditions are occasionally organized. The problem is the true value. The quality control, we need a duplicate measurements, 2 or more radon detectors at the same place, and the relative percent difference among the set is monitored. Field blanks, a set of detectors accompanying the exposed detectors to check whether the expected background level is in expected limit. How are alpha track detectors calibrated? I will show the example with a passive radon tone discriminative detector. Let me explain the characteristics of radiate again. Radiate collaboratively developed by our research group and Hungarian company. The shape is cylindrical. The inner volume is 30 cubic centimeter. They are quite small. The detecting material is CR39. 2 detectors used with different air exchange rate because of therefore therefore contamination can be eliminated. Etching condition and track reading system is the same as previous system. Body material is electroconductive plastic, and here is an electroconductive sponge as a filter instead of the filter. This device is quite small, so it is easy to transport by postal service and easy to place. This is an overview of our radon reference chamber. Exposure chamber. Yeah. Here is a sampling port to take air samples from the outside. You can see here is alpha guard in the chamber to monitor the radon concentration in the exposure chamber. We placed radiate like this way. And here's a fan to make a homogeneity of radon activity concentrations in the chamber. Also, from outside, we measure the radon concentration with a radon 7. Regarding integrating radon concentration versus alpha track density, time variation of radon concentration, temperature, and relative humidity in the radon chamber during an exposure test. It's the radon concentration, temperature, and relative humidity. Radon concentration was measured by alpha guard, pulse type ionization chamber, which was calibrated by PTB, Germany. After that, after taking radiate out of the exposure chamber, we proceed the data analysis and we got the result like this. The low air exchanger type, here is the time integrated radon concentration at the torque density. As you can see, the conversion factor for radon is the same. Yeah. This is a conversion factor. Same slope, 0.30321, 0.22 is the high air exchange rate type. Regarding iron tone chamber, as I mentioned in the previous slide, there's a humidity. Here's a humidifier, humidity control system. Here's the air. This is a Tolon gas generation unit and the grab sampling for calibration system. In our case, we use synthetic cells for intermittent measurement. For continuous monitoring, we use a radon 7 for radon tolon measurements, tolon concentrations, and also we measure the temperature and relative humidity in the chamber using the environmental monitor. This figure exemplifies the time variation of tolon concentration, temperature, and relative humidity in the tolon chamber during an exposure test. See, the tolon concentration is here by the violet purple color dot is given as a tolon concentration by radon 7, and red one, tolon concentration was given by scintillation cell. There's in a good agreement, as you can see. Blue line represents the relative humidity and temperature is here, almost stable. Regarding lower exchange rate type, it has low sensitivity against the tolon. That's why it's a quite small calibration factor, almost nothing. On the other hand, in the case of high air exchange rate radiate, we can obtain the calibration factor very clearly. There are conversion factors for radon and tolon concentrations by radiate in our institute from 2019 to last year, 2024. Here's a CR39 ID QRSH or something like this. Conversion factor is here. The low air exchange rate, high air exchange rate for radon, low, high for tolon concentration. See. Conversion factors for radon and tolon were estimated using radon and tolon chambers, our institute. But as you can see, the conversion factor is not the same. Every time we have to check the quality of detecting material like this. Using the radiate detector, we conducted several radon-tron survey in several countries. Japan, here. Mean radon concentration 22 becquerel per cubic meter, tron 22 becquerel per cubic meter. The ratio between tron and radon is 1.3. In Korea, South Korea, the radon concentration 62 becquerel per cubic meter, tron concentration 59. The ratio between tron and radon is 1.4. In Gansu, China, this area is famous for radon epidemiological study area. Radon concentration is 91 becquerel per cubic meter. But on the other hand, tron concentration is much higher than radon concentration, 365 becquerel per cubic meter. If we take the ratio between tron and radon, it was estimated to be 5.4. Yanjiang, China, as a high background radiation area, 37 becquerel per cubic meter for radon, 728 becquerel per cubic meter for tron. The tron to radon ratio is 35.3. In Canada, radon concentration 110 becquerel per cubic meter, tron concentration 76 becquerel per cubic meter. Radon-tron ratio is 0.97. Hungary, the radon concentration 208 becquerel per cubic meter. The tron concentration 128 becquerel per cubic meter. The mean ratio between tron and radon is 2.4. Tron interference on radon measurements, I will introduce this topic based on our experimental studies. As you may know, there are many types of passive radon detectors used in major epidemiological surveys. Here's the EPAM, this is the electrolyte. The German detector, Karlsruhe detector, which was used in the first survey in Japan. This is a European, this is a very popular radon detector in Europe. This radon track was used in the radon epidemiological study in China. Also, in France, they have two types of detectors, open detector and closed detector. This detector is similar to this. And also, Italy, they use the detectors sealed with polyethylene bag for tron entry control. Therefore, they can perfectly remove the tron contamination from radon signals. This table shows the relative sensitivities of passive radon detectors. Here's the measuring device, radiate low diffusion, that means low air exchange rate. It's a high air exchange rate type. Sensitivity for radon and toron. This is a prototype of radiate, namely Radopod. We modified the ordinary Hungarian monitor to measure the toron concentration. So we obtained higher sensitivity for toron. German detector, which was used in the first survey in Japan, it has a higher sensitivity for toron. Radiotrack, which was used in the radon epidemiological study in China, it has also higher sensitivity for toron, 68%. Regarding European detectors, popular detector, the toron sensitivity is quite low. Also, electrolyte EPAM has a lower sensitivity for toron. In Italian detector, as you see in the previous slide, by perfect sealing, they don't have any sensitivity for toron. Canadian detector used in the radon epidemiological study, it has also much low sensitivity for radon, about toron. And also I've explained the toron interference on radon measurement based on field experiences in epidemiological study area. We can explain the overestimate of radon concentration is like this. Observed radon concentration equals actual radon concentration plus relative sensitivity for toron times toron concentration. For example, when actual radon concentration and detected toron concentration are 100 becquerel per cubic meter respectively, radon concentration observed by Radiotrack is estimated to 168. Look at this. 0.68% sensitivity for toron compared to radon. Therefore, the detector reading give the 168 becquerel per cubic meter. One more thing I'd like to tell you, even when European detectors are used, their reading might be overestimated if they are placed near the wall as an indoor toron source. This slide shows the measurement of radon without discrimination derived from first national survey in Japan. We used the passive radon monitor German detector in the first national survey. We checked the performance of this detector like this. Here is a geometric arrangement of the monitor. Here is a soil wall in a house. This is indoor. And we place a passive radon monitor at a different distance from the soil wall, from 10, 20, 40, 80, and 140 centimeters distance from the soil wall. And then we obtained the detector response of the monitor. See? Here is a distance from the soil wall and radon concentration evaluated. The radon concentration close to the wall is higher than that of the center of the room. This is the reason why the radon concentration is higher. Radon concentration in the first survey is higher than that than expected. We found a total interference on radon measurements. We have to pay attention, special attention to radon measurement, especially if the area has high total potentials exist. We checked the performance of radiate. We checked the spatial distribution of radon and total concentration in a house with gypsum wall and a static condition, not the actual house, but the model room. This gypsum contains a relatively high activity, radium-226, 163, thorium-232, 522 becquerel per kilogram. We placed the radiate at different distance from the wall, gypsum wall. There's the radiate. And the result. As you can see, the radon concentration, red one, is stable regardless of the distance of the gypsum wall. On the other hand, total concentration varies in space. Actually, it's the distance from the gypsum wall. Here's the source of indoor radon and toron. Radon is a ground soil from a few meter depths, partially building materials. In the case of radium-rich material, radium-rich rocks are used in the building materials. The toron source, building materials, from a few centimeters thickness. Therefore, even a small quantity of toron source, a significantly high concentration might be given. I'd like to show you our survey in China. We visited cave dwellings in China. Many people at the time, this is around 2000, or between 2000 and 2005, we visited cave dwellings and we measured radon and toron concentrations in the cave dwellings. This is the schematic. And we placed the monitors in the center of the room. Here is a bed. People are sleeping there. And they cook inside of this room. There is a dimension. The length 8 to 10 meters. The height is 3 meters around. The width 3 meters. Here's one, it's a one-way house. So we visited this area, Gansu province. As I told you, in this area, radon epidemiological study was conducted. Here's the intercomparison of our survey result with the previous study. The radon concentration for previous study, they gave them more than 200 becquerel per cubic meter with a radon track. These are US detectors. As I pointed out, this device was affected by tone interference in radon measurements. Therefore, they didn't measure tone and tone progeny concentration. In our study revealed, the radon concentration is lower than previous study. 73 becquerel per cubic meter for radon, but tone concentration was high. Regarding tone progeny concentration, 2.4 becquerel per cubic meter. But odd ratio is here. Due to the small sample size of our study, I cannot say something strongly, but we need more study. We need more epidemiological studies here, if possible. Here are new implications and conclusions based on our study. Tone interference on radon measurements may result in incorrect risk estimate in several epidemiological studies on residential radon. Former studies might give us low risk estimate. So, according to WHO estimate, 20% risk is really correct? This is our question. Future studies or ongoing studies may give us high risk estimates. Therefore, radon concentration have to be accurately measured in any case. Quality assurance and quality control are one of the most important issues in the national radon strategy. So this is all my talk in this topic. Thank you.
Thank you very much, sir. Dear participants, if you have any question, you may please ask by unmuting yourself. Dear participants, if you have any question, please unmute yourself and you may ask the question.
Hello.
Yes.
Yes, Sanjeet, you may ask.
Hello. Hi, sir.
I can hear you.
Sanjeet,
Yeah, I have one. I have one small query that I just want to know that their radon has a specific contribution around 50, more than 50%, right?
Yes.
Among all
In the
the
worldwide average. Yeah.
yeah. So, what can be the contribution of the theron throughout the world average?
If my memory is correct, maybe less than 10% compared to radon.
Okay.
Yeah.
Okay, sir. So, and the next is usually we study about the radon. So, why thoron study is that much important, or why people neglected this one earlier?
For example,
I mean, what are the benefit and pros and cons of this thoron study?
okay, thank you for your question. Actually, in Europe or North America countries, radon concentration is much higher than Asian countries. But in Asia, as you see, there are relatively high thoron concentration were observed. Also, in order to analyze the risk due to radon isotopes, we have to measure both radon and thorium. Particularly, not thorium progeny need to be measured. Is my answer satisfactory?
Okay, okay, yes, sir. Thank you.
Any more questions, please? So if there are no questions from the participants, thank you very much sir, for this detailed and comprehensive talk. So we will resume this session again, the second session at 1:30 p.m. IST and 5 p.m. GST.
All right.
So participants will meet at the same Google Meet link at 1:30 p.m. IST. Thank you very much.
Thank you.
A warm greetings to everyone, and I Abhishek welcome back you again to second session of this day 4 of this GIAN course. So in this session, Professor Tokonami sir will continue to give his lecture in continuation to his previous lectures, and he will be delivering his talk on regulations of norms. So I invite Professor Tokonami sir to deliver his talk.
Thank you for your introduction. Can you hear me?
Yes, sir, I can hear you.
Okay. How about my slide?
Yes, sir, your slides are visible, sir. You can make it just move.
Move?
Yes, sir,
Moving?
the slides are moving. Yes, sir.
Okay. So I have last two lectures today. The first one, I would like to talk about regulations of norm. What is norm? Norm is a naturally occurring radioactive material. Radioactive material containing no significant amount of radionuclides other than naturally occurring radionuclides. The exact definition of significant amount would be a regulatory decision. Material in which the activity concentrations of the naturally occurring radionuclides have been changed by a process is included in naturally occurring radioactive material. Naturally occurring radioactive material or norm should be used in the singular unless difference is explicitly being made to various materials. Radioactive material is a material designated in natural law or by a regulatory body as being subject to regulatory control because of its radioactivity. This is from the IAEA safety glossary, terminology used in the nuclear safety and radiation protection. Regarding radiological properties, a total of 36 radionuclides are present in the three natural radioactive decay series: uranium-238, uranium-235, and thorium-232. Analyzing known materials requires determining which radionuclides need to be identified and quantified. The focus is primarily on long-lived radionuclides. Non-radiological aspects. Materials may contain acid-forming minerals. The solubility of the host materials should be considered. The tendency of the material to form dust is also significant. Here is a decay chain of uranium series, thorium series, and actinium series. Regarding radiological properties, focusing on long-lived alpha emitters, they are uranium series such as uranium-238, uranium-234, thorium-230, radium-226, lead-210, and polonium-210. Thorium series, thorium-232, radium-228, and thorium-228. Gamma emitters, thallium-208, actinium-228, radium-226, etc., and potassium-40. Focuses on radon, toron, and their decay products. Characterization depends on the type of material being analyzed. For unprocessed materials, the uranium and thorium decay chains are typically assumed to be in circular equilibrium, requiring an analysis of only the parent radionuclides, such as uranium and thorium. For processed materials, it is necessary to determine which radionuclides are present and their concentrations. Health hazard of norm. The main health risk of norm is cancer, as its ionizing radiation is carcinogenic. Increased exposure raises cancer risk slightly. Personnel can be exposed to radiation emitted by norm in two primary ways. What's one? Irradiation. Exposure occurs when radiation is emitted by materials located outside the body. Second, contamination. Due to inhalation or ingestion of material containing radionuclides, such as dust particles, we need to consider this contamination. All beginning materials, natural radioactivity of the beginning materials. All beginning materials contain various amounts of natural radioactive nuclides. Materials derived from rock and soil contain mainly natural radionuclides of the uranium-238 and thorium-232 series, and the radioactive isotope of potassium-40. In the uranium series, decay chain segment starting from radium-226 is radiologically the most important. Here is a typical and maximal activity concentration in common buildings, materials, and industrial byproducts used for building materials in the European Union, EU. Material, most common buildings, typical activity concentration with radium-226, thorium-232, potassium-40, and the maximum activity concentration. Concrete has 40 becquerel per kilogram, 30 thorium, 30 becquerel per kilogram, potassium-40, 400 becquerel per kilogram. As a maximum activity concentration, in the case of concrete, 240, thorium-232, 190, for potassium-40, 1,600 becquerel per kilogram. Aerated and lightweight concrete, 60 for radium-226, 40 for thorium-232, 430 for potassium-40, 2,600 becquerel per kilogram for radium-226, 190 for thorium-232, 1,600 for potassium-40. Clay bricks, as a typical value, 50 for radium-226, 50 for thorium-232, 670 for gallium-40, potassium-40, as a maximum activity, 200 becquerel per kilogram for radium-226, 200 becquerel per kilogram for thorium-232, and 2,000 becquerel per kilogram for potassium-40. Sandline bricks. This is lower than other common other building materials. 10 becquerel per kilogram for radium-226, thorium 10 becquerel per kilogram, 330 for potassium-40. Even as maximum activity, (25 becquerel per kilogram as radium-226, thorium 30, and potassium-40, 700. Natural building stones, 60 radium-226, 60 thorium-232, 640 for potassium-40. As maximum activity, in the case of natural building stones, 500 for radium, 310 for thorium, and 4,000 for potassium. In the case of natural gypsum, the activity is relatively low, which is comparable to sand lime bricks, 10 for radium, 10 for thorium, and 80 for potassium-40. As maximum activity, 70 for radium, 100 for thorium, and 200 for potassium. Common industrial byproduct used in building materials. Byproduct gypsum, phosphogypsum, as you can see, the radium contents, radium activity is much higher than others, which are concentrated 390 becquerel per kilogram for radium-226. In the case of thorium, 20, the potassium 60, as a maximum 1,100. In the case of thorium, 160, the potassium-40, 300. Blast furnace slag, 270 for radium-226, 70 becquerel per kilogram for thorium-232, and 240 for potassium-40 as a typical activity. As maximum activity, 2,100 for radium-226, 340 for thorium-232, 1,000 becquerel per kilogram for potassium-40. Coal fly ash, as a typical value, 180 for radium, 100 thorium, for thorium and 650 for potassium, 1100 for radium, 300 for thorium, 1500 for potassium 40 as a minimum activity concentration in becquerel per kilogram. Here are examples of the annual effective dose due to external exposure. First, we classified into 4 categories: low activity material, average concrete, upper level of normality, and enhanced concentrations. In this low activity materials, 10 becquerel per kilogram of radium, 10 becquerel per kilogram of thorium-232, 300 becquerel per kilogram of potassium 40. When we calculate the annual excess dose based on structures in a building causing the irradiation, floor, ceiling, and walls, all structures contains these radioactivities. The level is less than background dose, floor and walls, namely wooden ceiling, floors only, that is wooden house with concrete floor. Both are less than background dose. At average concrete, average value, in this case, floor, ceiling, and walls contains this radioactivity. It gives 0.25 millisievert per year. Floor and walls, 0.1 millisievert. Floor only, less than background dose. If we take radioactivities with these values, when we calculate annual excess dose, floor, ceiling, and walls gives 1.1 millisievert. Floor and walls gives 0.74 millisievert. Floor only is 0.11 millisievert. Finally, enhanced concentration at the maximum radioactivity with these values, the annual excess dose was calculated to be like this. Floor, ceiling, walls 2.3 millisievert per year. Floors, walls 1.6 millisievert. Floor only 0.41 millisievert. Parameters values used in calculating the dose. Here is a table for the calculation, dose calculation. Dimension of the model room, 4 meters by 5 meters by 2.8 meters. Thickness and density of the structures, to 20 centimeters to 1,350 kilogram per square cubic meter. Annual exposure time, 7,000 hours. Dose conversion is given as 0.7 millisievert per gray. Background 50 nanogray per hour. Specific dose rate, nanogray per hour per becquerel per kilogram. Look at here. Structure in a building causing the irradiation. Floor, ceiling, and walls 0.92 nanogray per hour. 1.1 nanogram per hour per becquerel per kilogram, like this. Fluors only 0.24 for radium, nanogram per hour per becquerel per kilogram. .28 for thorium-232, nanogram per hour per becquerel per kilogram, 0.02 nanogram per hour per becquerel per kilogram. Superficial material, tiles or stones on the walls, thickness of 3 centimeters and density 2,600 kilogram per cubic meter. 0.12 for radium, 0.14 for thorium-232, and 0.0096 for potassium-40. I'm talking about building materials and radon. The internal exposure is caused by the inhalation of radon, thorium, and their short-lived progeny. Radon is part of the radioactive decay series of uranium, which is present in building materials. Because radon is inert gas, it can move rather freely through porous media, such as building materials. The most important source of indoor radon is the underlying soil, but in some cases, the building materials may be an important source. In most cases, the main part of indoor radon on the upper floors of a building originate from building materials. Typical excess indoor radon concentration due to building materials is about 10 to 20 becquerel per cubic meter in some regions, in some zones, and in rare cases, it may rise up to greater than 1,000 becquerel per cubic meter. Wait a moment. Radiation protection principles. The purpose of setting controls on the radioactive building materials is to limit the radiation exposure due to materials with enhanced or elevated levels of natural radionuclides. The dose to the general public should be kept as low as reasonably achievable, ALARA. Since small from building materials are ubiquitous, controls should be based on exposure levels which are above. Above typical levels of exposures and their normal situations. Okay, wait a moment. I have to change. Sorry. Okay. Since of small exposure from building materials ubiquitous control should be based on exposure levels which are above typical levels of exposures and their normal situations. all buildings contain some natural radioactivity. Small unavoidable exposures need to be exempted from all possible controls. Restricting the use of certain building materials might have significant economical, environmental, or social consequences locally and nationally. Such consequences, together with the national levels of radioactivity in building materials, should be assessed and considered when establishing binding regulations. The amount of radium in building materials should be restricted at least to a level where it is unlikely that it could be a major source for exceeding the design of level for indoor radon introduced in the Commission recommendation with 200 becquerel per cubic meter. Regarding controls on the radioactivity of building materials, based on the following radiological criteria and principles, those criterion for controls should be based on a dose criterion which is established considering overall national circumstances. Controls can be based on a lower dose criterion if it is judged that this is desirable and will not lead to impractical controls. It is recommended that the controls should be based on a dose in the range of 0.3 to 1 millisievert per year. Note that this is the excess gamma dose to that received outdoors. As exemption level, building materials should be exempt from all restrictions concerning their radioactivity if the excess gamma radiation originating from them increases the annual effective dose of a member of the public by 0.3 millisievert at the most. Note that this is the excess gamma dose to that received outdoors. Separate limitation for radon or thoron exhaling from building materials should be considered where previous evaluations show that building materials may be a significant source of indoor radon or thoron. Here are the investigation levels for practical monitoring purposes. It is practical to present investigation levels in the form of an activity concentration index. You can see this formula. The activity concentration index should take into account typical rates and amounts in which the material is used in a building. The following activity concentration index is derived for identifying whether a dose criterion is met. Dose criterion here, materials used in bulk amounts, such as concrete, superficial and other materials with restricted use, such as tiles, boards, etc. Dose criterion when the dose criterion is 0.3 millisievert per year, index is less than 0.5. Criterion of 1 millisievert per year, index should be less than 1. In the case of superficial and other materials with restricted use, in the case of 0.3 millisievert per year, ion index less than 2. In the case of 1 millisievert per year, index should be less than 6. How is the index derived? The activity index is derived to indicate whether the annual dose due to the excess external gamma radiation in a building may exceed 1 millisievert. The activity index is calculated like this. Factor for radium dose criterion 1 millisievert per year equals sievert per 10 to minus 3 minus third, and calculated. The factor for thorium, the radium is eventually concentration will be 276 becquerel per kilogram. Then after rounded value is 300 becquerel per kilogram. Factor for thorium. Criterion 1 millisievert per year is thorium 232 concentration is here, and eventually thorium concentration will be 231 becquerel per kilogram. The rounded value is 200 becquerel per kilogram. Here's a potassium. This is wrong. Potassium body, the same manner as previous two equations. The potassium 40 concentration will be 3,176 becquerel per kilogram. Rounded value 300 becquerel per kilogram. So the index can be written like this. Here is a 0.92, 1.1, and 0.08 are coming from this one. Specific dose rate, coefficient. Here is important information. The activity concentration index should be used only as a screening tool for identifying materials which might be of concern. Any actual decision on restricting the use of a material should be based on a separate dose assessment. Such assessments should be based on scenarios where the material is used in a typical way for the type of material in question. Scenarios resulting in theoretical, mostly unlikely maximum doses should be avoided. Here is a flowchart of the recommended system of control of building materials. First, determine activity concentration of radionuclides in the building materials. Then, determine the activity index. If the index is less than 1 or 6, no restrictions. If not, first assess the dose. If the dose is less than reference level, namely 1 millisievert, that you we don't have to do anything, no restrictions. If not, dose is more than reference level of 1 millisievert. Decide on appropriate measures. This slide shows the gamma radiation from building material. Sorry. Gamma radiation from building materials in existing building materials. Buildings. Protective actions may be necessary for existing buildings with high annual effective dose levels caused by gamma radiation due to radionuclides in the building materials. If considered necessary, the national authority should establish different levels for exposure to gamma radiation emitted from building materials in existing buildings. Feasible protective measures are not easy to implement. The national authority should consider requiring protective actions to be mandatory for existing buildings of high occupancy where the effective dose levels exceed 100 millisievert. Note that the protective measure carries serious economic and penalties and should not be applied without careful consideration. Here's the role of building material as an indoor radon source. How does radon release from building materials? This is a feature of radon. Feature on radon comes from soil and rocks and building materials. Here is a equation of the acceleration rate. This is the diffusion length. Effective diffusion coefficient is dominated by transport, which is an important parameter for transport and emanated radon. Radium decay, emanation, the diffusion, and acceleration from surface to the atmosphere. Here is the emanation coefficient, F, is a dimensionless. The ratio between the escape radon into pore space to the total amount of generated radon. Radon is generated from radium in soil, rocks, and building materials. Therefore, radium concentration is important. Here's the equation reported in ANSCA 2000. Radon acceleration rate from the soil surface is written by this equation. Radium-226 concentration, decay constant of radon-222, emanation coefficient, density of the soil, the porosity of the soil, and diffusion length. There are important parameters to determine the acceleration rate. This table shows different materials and emanation coefficient and diffusion length. Concrete, 0.1 to 0.4, the emanation coefficient, 0.06 to 0.2 as diffusion length. Brick, 0.02 to 0.1 emanation coefficient 0.2 to 0.4. Gypsum 0.03 to 0.2. 0.8 to 1.3 as diffusion length. Cement. The emanation coefficient is quite small compared to other three, especially other concrete. Cement 0.02 to 0.05. No data on diffusion length. Fly ash also much smaller than others. Then this is a typical exhalation rate from various building materials. In the case of concrete, 2 to 30 becquerel per square meter per hour. The surface radon exhalation rate. Byproduct gypsum 5 to 40. Aram shell concrete 50 to 200. Lightweight concrete 1 to 3. Brick 2 to 5. Here is a table on the various materials and mass exhalation rate expressed in becquerel per kilogram per hour. The concrete 0.002 to 0.1. The brick 0.001 to 0.05. Aram shell concrete 2 to 3. Natural gypsum 0.002 to 0.02. This slide describes the contribution to indoor radon concentration from different building materials. Using this formula, this is C, radon concentration, E, exhalation rate per unit area, surface exhalation rate, and S, exhaling area. B, room volume. Lambda V is air exchange rate, ventilation rate of the room. Here are the various materials. Concrete, we assume the exhalation rate of 10 becquerel per square meter per hour. The maximum radon concentration will be 40 becquerel per meter. Realistic value 20. Lightweight concrete, when we assume the acceleration rate of 2, the radon concentration will be 7 as maximum, 4 as realistic value. Aram shell concrete, if we assume the acceleration rate of 200 becquerel per square meter per hour, the radon concentration goes up to 700 becquerel per meter, and realistic value is 400 becquerel per meter. Clay brick, when we assume the acceleration rate of 4 becquerel per square meter per hour, the radon concentration will be 15 becquerel per meter as maximum, and 5 becquerel per meter as a realistic value. Byproduct gypsum, when we assume the acceleration rate 20 becquerel per square meter per hour, the radon concentration will be 70 as maximum, 10 as realistic value. This slide exemplifies the experimental setup for mass exhalation rate measurement. So in our laboratory, we use a scintillation cell. we placed the building materials in the chamber, accumulation chamber here. And we took the samples, air samples, to situation cell and measure the radon concentration. There is an equation to determine that this is F means emanation coefficient. AE, the radon concentration in equilibrium condition. A, radium concentration in building materials. Volume is accumulation chamber, and W, mass of sample. I will show some data, natural radioactivity concentrations at industry sectors. Petroleum, oil and gas here. Produced water, the radium-226, 612 becquerel per gram. Becquerel per kilogram, and scale 611 for both radium-226 and radium-228. In the mineral processing, the highest value gives with a discard byproduct. In the case of radium-226, it's 3,130 becquerel per kilogram. Radium-228, 8,460 becquerel per kilogram. In the case of water treatment, sediment is the highest, maybe the highest. But compared to other materials, other activity, it's not so high. Radium-226, the 64 becquerel per kilogram. Radium-228, 108. And here is a mineral dressing, zircon and tantalum. Yeah. In the case of zircon, it's much higher than other material. Phosphate production, phosphogypsum gives a high radioactivity of radium-226, 750 becquerel per kilogram. Oil and natural gas production. During the extraction of oil and natural gas, the natural radionuclides from underground formations are brought to the surface. Elevated activity to radium present in NOM are often released by oil and gas industry, particularly in production waters. During the extraction process, radium is precipitated along with barium and strontium. A portion of the radium is deposited during the scale formation process, and other portion is discharged to the sea with effluent ends. The most important radionuclide in scales and other participants are the isotopes of radium with specific activity ranging from 100 to 1000 becquerel per kilogram. Concentrations of lead-210 and polonium-210 in sludge and scales can vary between 20 and 1,000 becquerel per kilogram. The disposal of scale from oil extraction industry installation and of sludge containing known can be of environmental significance, with contamination of land being the major concern. For example, the average radium concentrations in soils sampled at an oil field contaminated with known on Western Kentucky, United States, were 32,560 becquerel per kilogram. Bauxite and aluminum industry. Bauxite is used to produce alumina, which is then used to produce aluminum. Waste can be generated at several points in the production process. Bauxite ores sometimes contain elevated concentrations of natural uranium and thorium. Volume is reduced by half, but majority of radionuclides report to mud. Mud contains radionuclide concentrations above background levels. Internationally, only about 2 to 3% of bauxite residuals are reduced in a productive way. Phosphate industry. Phosphate rocks is used extensively, firstly as a source of phosphorus for fertilizers and secondly for making phosphoric acid and gypsum. Ores typically contain about 1,500 becquerel per kilogram of uranium and radium. The fertilizers become somewhat enriched in uranium up to 150% relative to the ore, while 80% of radium, 30% of thorium-232, and 5% of uranium are left in the phosphogypsum. Phosphate industry. The use of phosphate fertilizers in agriculture and of gypsum in building materials is a further source of possible exposure of the public. Elevated radon exposure of the public can further be expected in sites being developed for housing. The slug, which contains radium-226 concentrations ranging from 750 to 1,100 becquerel per kilogram, has been used as building material in the United States, especially communities in southeast Idaho. Coal mines and processing. The average specific activity of both uranium-238 and thorium-232 in coal is generally around 20 becquerel per kilogram, ranging from 5 to 300 becquerel per kilogram. During the burning of coal, the organic compounds are converted into gases, while the inorganic elements, which include the significant naturally occurring radionuclides, are concentrated in the ashes. In general, the radionuclide enhancement factor in ash is about 10. Leaching from fly ash is low, and therefore there are few restrictions on the use of fly ash in landfill and road construction. The use of fly ash for building construction results in radiation exposure from both direct irradiation and radon exhalation. Dumping fly ash may increase the radiation level around the dump site. The most significant exposure pathways are ingestion and inhalation of the isotopes lead-210 and polonium-210. Building industry, extensive use of non-reduce fly ash produced in large quantities from coal burning, sludges of steel works and metal recycling industries, phosphogypsum, red mud of the aluminum processing industry. Extensive use of non-residue fly ash produced in large quantities from coal burning, sludges of steel works and metal recycling industries, phosphogypsum, red mud of aluminum processing industry. None in materials is source of gamma radiation. Radon exhalation also the potential source of exposure. Exposure scenarios, longer times are necessary. Rare earth and titanium oxide industries. Lantanoid rare earth metals has 6 elements. Bastnasite and monazite are the most important minerals containing rare earth metals. Activity concentration is bastnasite 900 to 1,200 becquerel per kilogram for uranium-238 decay series, 700 to 7,000 becquerel per kilogram for thorium-232 decay series. Activity concentration of monazite, as you know, 10,000, much higher, 10,000 to 50,000 becquerel per kilogram for uranium decay series, 5,000 to 350,000 becquerel per kilogram for thorium-232 decay series. Rare earth titanium, the same titanium oxide industries. Activity concentration of titanium ore 300 to 600 becquerel per kilogram for uranium-238 series, 35 to 600 becquerel per kilogram for thorium-232 decay series. For titanium production, specific activities of radium sulfate participate in pigments or scales may be as high as 400,000 becquerel per kilogram, and thorium-228 levels may be higher than 1 times 10 to 6 becquerel per kilogram. Exposure pathways include external irradiation and the immigration of radionuclides from landfill. Here is an example of the measurement at rare earth extraction plant in Thailand. Actually, we made this measurement in the rare earth extraction plant. High gamma dose rate was observed at Department of Waste Management. The value is 6.3 microgray per hour. The average gamma dose rate was 0.43 microgray per hour. average gamma dose rate nearby the plant, around the plant, is this normal level, 22 nanogray per hour. High radon and thorium concentration were observed, but uranium radon levels more than 400 becquerel per cubic meter, and thorium concentration more than 5,000 becquerel per cubic meter. Professor Mera, may I have a short break?
Hello.
Hello, may I have a short break?
Sir, not able to hear you.
Excuse me?
Yes, sir.
Yeah.
So, dear participants, if you have any question, you may unmute yourself and ask a question. So, in case participants do not have any question, we will be taking a break of 10 minutes, and we will be joining the meet again to resume the session at 2:40 p.m.
Okay.
So, after 10 minutes, we will resume the session.
Okay. All right.
Yeah, yes, sir. Dear participants, welcome back after a short break. Professor Tokunami sir will be resuming his lecture again in this second session. So I invite Professor Tokunami sir to again resume his lecture on radon and thoron.
Thank you. Can you hear me? Can you hear me?
Yes, sir, I can hear you.
Okay.
Yeah, hello.
So I will explain about IAEA guidelines, general safety requirements, part 3. As you know, there are 3 exposure situations, namely planned exposure situation, existing exposure situation, and emergency exposure situations. Then we have 3 categories of exposure. That is, they are occupational exposure, medical exposure, and public exposure. This document covers all the situations and all the exposures. ICRP recommendations. The ICRP previously differentiated between practices that increase doses and interventions aimed at reducing them. In its 2007 recommendations, the ICRP adopted a situation-based approach to classify potential radiation exposure scenarios into 3 categories: existing, planned, and emergency exposure situations. It applies a unified set of fundamental protection principles to all these scenarios. Basic safety standards on known as a criteria for the regulation. Exposure to natural sources is normally considered as an existing exposure situation. If the activity concentration of any radionuclide in the uranium or thorium decay chains exceeds 1 becquerel per gram, or potassium-40 exceeds 10 becquerel per gram, apply requirements for planned exposure situations. Okay. Exposure to radon in workplaces. Radon exposure is typically not regulated as a standard practice, but is managed under the guidelines for existing exposure situations. The reference level for radon shall be set at a value that does not exceed an annual average activity concentration of radon of 1,000 becquerel per cubic meter, with account taken of the prevailing social and economic circumstances. Occupational exposure to radon is regulated under the requirements for planned exposure situations in the following cases: when exposure to other radionuclides from the uranium and thorium series is already managed as a planned exposure situation; when, despite the remedial actions, radon concentration remain above the established reference level. A worker's load depends on the type of work, non-activity, time, and protective measures. It is crucial that all individuals involved in managing known equipment and waste possess the required competence and awareness of the associated risks, work systems, and control measures. This includes managers, radiation safety officers, safety engineers, technical engineers, supervisors, technicians, and others. Control gamma exposure. Non-material emit gamma radiation and require monitoring. Facility designs ensuring adequate distance, providing shielding with walls, and etc. Workplace practices, developing rules and procedures to manage exposure durations. Safety measures, utilizing warning signs and physical barriers to enhance protection. Control radionuclides in airborne dust. Airborne contamination can occur wherever dry materials are handled or processed. Spills and the spread of materials to other areas usually pose no radiological concern unless the activity concentration are sufficiently high. Dust sampling involves taking a sample of air through a filter medium. Workplace ventilation is often implemented to control dust, which may already be regulated by occupational health and safety standards for non-radiological reasons. For control radon exposures, ventilation, particularly in underground mines, ventilation is crucial. Occupancy time. In case where there are practical limitations on providing sufficient ventilation, occupancy time may need to be managed. Workplaces with high thorium-232 contents. Additional measures may be necessary to control thoron. Regarding transport of norm, the guidelines are encapsulated in the IAEA Safety Standard Series, number SSR 6 regulations for the safe transport of radioactive material. Norm is classified as radioactive material. However, not all norm falls under the scope of the transport regulations. The scope of application of the transport regulations to norm depends on activity concentrations and whether or not the radionuclide content is incidental to the use of the material. The purpose of transport regulations for radioactive materials, including natural occurring radioactive material, is to ensure the safe and secure transport of such materials while minimizing risks to human health, property, and the environment. Contaminant of radioactivity, control of external radiation levels, covered all radioactive materials. Not in Japan. Japan is deficient in mineral resources and most mines for various resources except limestone and small number of precious metal. The significant issue on norm regulation would be exposure of workers handling various types of industrial raw materials. The estimated annual effective dose was below 1 millisieverts per year, which aligns with the dose criterion outlined in the international BSS basic safety standard for the exemption of bulk materials containing natural radionuclides. However, the annual effective dose exceeded 1 millisievert per year in only the most critical scenario where a worker handled metals materials with natural radionuclides from the thorium-232 series at concentration exceeding several hundred becquerel per gram. The summary of this lecture: known is present across various industries. Every industry has unique characteristics and specific exposure scenarios. It is crucial to develop a comprehensive understanding of each industry to address norm effectively. Offering professional training courses for workers and employees handling non-contaminated facilities is vital to ensure safety and compliance. So here is the last lecture for my talk. Fukushima nuclear accident. In 2011, we had a big earthquake. See, this was the fourth most powerful earthquake recorded in the world since 1900. The time, 2:46 p.m. on Friday, March 11th, 2011. Epicenter 72 kilometers east of Oshika Peninsula here, of Tohoku region. Magnitude was 9. Duration was 6 minutes. Here's the epicenter. This is Fukushima nuclear power plant. The Tokyo is far from 220 kilometers far from the Fukushima Daiichi nuclear power plant. Here's a photo. A 3-story building collapsed by the earthquakes in Sukagawa City, Fukushima, on March 11. The height of tsunami is more than 10 meters. The place, the Pacific coastline of Japan's northern island. On March 11th, 3:15 p.m., tsunami struck Onahama Port on Iwaki City, Fukushima. Fishing boat and vehicles were carried away. This was the land. Here is the geographical situation of Fukushima Daiichi nuclear power plant. Onagawa was a nuclear power plant closest to the epicenter of the earthquake, but it was not significantly affected by the tsunami, and it was quickly taken to cold shutdown. The one operable reactor at Tokai also reached cold shutdown without any incident. 2 reactors at Fukushima Daini experienced pressure control problems, but eventually all 4 reactors reached cold shutdown. Only Fukushima Daiichi nuclear plants were affected. Unit 3 and Unit 4 at Fukushima Daiichi nuclear power plant were destroyed by a hydrogen explosion and fire. This photo was taken on March 15, 7:30 a.m. See, here's the damage by tsunami at Fukushima Daiichi. Here is the Fukushima Daiichi event sequence. date March 11, 2:40 p.m., the 9.0 magnitude earthquake strikes. Ground acceleration triggers automatic shutdown of all 3 reactors in operation. A 14-meter tsunami triggered by the earthquake disables all AC power to Unit 1, 2, and 3 at 3:42 p.m. At 3:45 p.m., fuel tanks for emergency diesel generators are carried off by the tsunami. At 4:46 p.m., water infection fails in the emergency core cooling systems of Unit 1 and 2. Date March 12. At 9:07 a.m., a pressure relief valve is open on the Unit 1 pressure vessel. 3:36 p.m., a hydrogen explosion damages the structure of the Unit 1 reactor building. At 8:20 p.m., seawater injection to the Unit 1 pressure vessel begins. On March 13, water injection fails in the emergency core cooling system of Unit 3 at 5:58 a.m. At 9:20 p.m., a pressure relief valve is open on the Unit 3 pressure vessel. Water injection fails in the emergency core cooling systems of Unit 1 and Unit 2. Note that events in red letters are closely related to the release of radioactive materials into the environment. On March 14, at 11:01 a.m., hydrogen explosion damages the external structure of the Unit 3 reactor building. The seawater level in the Unit 2 pressure vessel is found to be low, leading operators to conclude that reactor cooling is no longer functional. At 1:25 p.m. At 4:34 p.m., seawater injection into Unit 2 pressure vessel begins. On March 15, an explosive sound is heard at Unit 2, and it concluded to indicate an abnormality in the pressure suppression pool. At the same time, a part of a wall, the operation area, Unit 4, is damaged at 6:20 a.m. At 9:38 a.m., a fire breaks out in the Unit 4 reactor building. The Unit 4 fire is extinguished at 12:29 p.m. On March 16, at 8:37 a.m., a large quantity of white smoke issues from Unit 3 reactor building. On March 17, Self-Defense Force helicopters drops water on the Unit 3 reactor building for the first of 4 times. 9:48 a.m. At 7:05 p.m., a police water cannon truck begins injecting water into the Unit 3 reactor building. Self-defense pumper trucks begin injecting water into the Unit 3 reactor building for the first of 5 times at 7:35 p.m. On March 18, at 10 a.m., it is confirmed that the common spent fuel pool for Fukushima Daiichi is filled with water, and no abnormalities are observed in the spent fuel dry cask storage buildings. This table shows the radioactive materials released from Fukushima Daiichi nuclear power plant. The half-life, decay of type of decay and emitters and radionuclides. Inert gas, krypton and xenon, volatile elements, iodine-131. This is most significant radionuclides for the general public under the emergency situation. And here is a cesium, radioactive cesium, 134, 136, 137. A radioactive material released from the Fukushima Daiichi nuclear power plant. Here is the monitoring data around Fukushima. The unit is microsievert per hour. A large amount of radioactive materials were carried into the northwest direction. Here is the Fukushima Daiichi nuclear power plant, and we found the highest gamma dose rate here, measured on March 20. In Fukushima, it began to rain and snow on March 15 afternoon. Here are time variations of radiation monitoring data in two cities, Fukushima City and Tokyo. On March 15th afternoon, gamma dose rate suddenly increased in Fukushima City. It is considered to be due to rainfall, that is, wet deposition of radioactive materials. Several peaks of the gamma dose rate were found in Tokyo. A radioactive plume passed through the city. When another plume passes through the city, it rained and consequently radioactive materials deposited on the ground. Here is a simple data analysis for radionuclide fraction consisted by ambient gamma dose rate in Fukushima City. We have a data on time variation of ambient gamma dose rate measured in Fukushima City here. Elapsed day, elapsed time, and dose rate. In order to estimate a radionuclide fraction, we need assumptions, several assumptions. The following radionuclides were consisted of by the ambient gamma dose rate: Thorium-132, iodine-131, iodine-132, cesium-134, 136, and 137. For analysis, after considering the half-life of each radionuclide, monitoring data were estimated with potential curve fittings. As a result, about 80% of gamma dose rate observed on March 17, 2011 was estimated to be derived from Thorium-132 and its progeny, iodine-132. This fraction is close to another measurement and analysis with 63%. It's similar. Terrestrial pathways of transfer of radionuclides and dose to humans. Radioactive materials go to the air, and by external exposure, human people receive the dose. By inhalation, the people receive the dose to the body. by deposition, radioactive materials placed on the surface of soil. And by transfer through the crops, here's the diet contaminated with radioactive materials. By ingestion, people take the radioactive materials and eventually receive the dose. Main pathway of internal exposure in Fukushima nuclear accident. Inhalation is higher possibility. Ingestion is lower possibility due to quick countermeasures on foodstuff. Regardless of ages, many people might have taken radioactive materials. When the radionuclides are taken into human bodies, iodine deposits in thyroid. Strontium deposits in bones because its behavior is similar to calcium. When plutonium is inhaled, it deposits in lung and bone. Cesium is soluble to blood and is distributed in the whole body, such as muscle. Some of radioactive materials are excreted by metabolism. Here is the biological half-life. Iodine 80 days, cesium 70 to 90 days. In the case of strontium and plutonium, the biological half-lives are much longer than others because they deposit in the bone. On March 13, the Radiation Safety Council at Hirosaki University convened to discuss a policy in response to the nuclear accident. At the request of the Japanese government, the council decided to dispatch our university staff members to Fukushima to assess residents in the area. The first, our team, Hirosaki University team, was sent to Fukushima on March 15. Two important projects are involved, namely screening tests for radioactive contaminations among the general public in Fukushima Prefecture, temporary home visit within the 20 kilometers evacuation zone for displaced residents. Another significant initiative in Fukushima involved fieldwork focused on radiation measurements and sampling to help reconstruct exposure doses. Here is a related article from the local newspaper. This is me. I was saying something in front of our president. As a screening test for radioactive contamination is defined as the presence of radioactivity in unwanted area. Contamination occurs when a radioactive material is deposited on or in an object or a person or a place. GM survey meter was used for the screening test. Contamination means count rate exceeds 100,000 ppm. In this case, decontamination is needed. In the case of partial contamination, count rate is between 13,000 and 100,000 ppm. In this case, decontamination is suggested. No contamination count rate does not exceed 13,000 CPM. In this case, no decontamination is needed. Twenty teams from our university were dispatched to Fukushima until the end of July 2011. Eventually, more than 5,000 people in Fukushima was inspected. Also, in parallel with such activity, we carried out a survey, carbon survey along an expressway. Here is our city, Hirosaki, and here is Fukushima, and Fukushima nuclear power plant. Those rate measurements were made on March 16, April 11, and April 25. Distance from nuclear power plant to measuring point 60 to 355 kilometers. We used a detector of 1-inch sodium iodine scintillation survey meter here. Measurement time is every 1 minute, and also we recorded the location, geographical location, using the global positioning system. Eventually, more than 100 measurement data were obtained. Also, we estimated the shearing effect by car body, 1.9 with 56 data. Also, we made a comparison between pavement and unsealed surfaces. Here is the data result of our carbon survey. Distance from Fukushima nuclear power station and dose rate in air. We started here from Hirosaki to Fukushima. As you can see, after accident, for example, March 16, the ambient dose rate in air increased rapidly as we approached Fukushima very highly. In the first survey, dose rate increased rapidly 0.08, this is a natural level, to 11 microsievert per hour. The second and third surveys difference dose rate profile along the expressway. Obvious difference is found around Oshu City. Dose rate differs by a factor of 10 between first survey and second survey. Second is here, green. Before, fortunately, we have the background data on the expressway here. Also, the number data is small. Yeah, this is actual data. The black line represents for the theoretical calculation based on the natural radioactivity concentration from the geological data. Difference data before accident were obtained by 12 years old boy, my son, together with me. He measured gamma dose rate along the expressway in August 2010 with me. This is the first contact of radiation for my son. My son provided a data, precious data on the back as a background, but we didn't put his name as a co-author. This is a paper based on our survey time variation of dose rate artificially increased by the Fukushima nuclear crisis. So 2011, June. My son is missing. After 15 years, we have a co-authored paper. My son, he's studying about transparent X-ray shielding solutions. So we, son and I, published a paper, SES Omega, very recently. So we measured gamma spectrometry in Fukushima accident. As you can see, this is a very unique alpha gamma energy spectra. We found a lot of gamma peaks. Thorium-132, iodine-131, cesium-137, 134, like this. We use a 3 inches sodium iodine scintillation detector. So we examine the fraction of gamma dose rate. You see, this city is located in the northern west. The first plume reached this area. You see, the most significant contribution is iodine-132 produced by thorium-132. But this city is located south of nuclear power plant. The pattern, color pattern is different from 3 areas. The main contributor is iodine-131. That means the different plume reached this city. Also, the components of the other plume is different from the first one. But here is a result on the gamma dose rate at screening venues from March 16 to May 27. Here's outside the outdoors in Fukushima. More than 13 microsievert per hour is not normal. Red one is indoor dose. Indoor dose much smaller than outdoor dose rate. Also, we recorded our personal dose using this device, digital dosimeter. The highest dose is approximately 100 microsievert. I received this dose. I was the highest. Also, we carried out a siloed study. More than 6,000 people evacuated from the coastal areas in Namie Town and State Tsushima District from March 12 to 15, 2011. Yeah. Radioactive plume reached Tsushima District. Actually, radioactive plume passed through like this way, this direction. And the radioactive reached Tsushima district in the afternoon of March 15. We measured the radioactivity, gamma rate, dose rate from iodine 131 using sodium iodine scintillation spectrometer. Measurement period April 12 to 16. The number of measurement 45 evacuees from coastal area and 17 residents. Totally 62 persons are inspected. The range of age 0 to 83 years old. The measurement time is 5 minutes. Here's the result. Thyroid equivalent dose due to iodine intake. The over 20s, 74% were detected. The range LD to 33 millisieverts. Median value is 3.5 millisieverts. For children less than 19 years old, 75% detected. Range LD to 23 millisieverts. Median value is 4.2 millisieverts. This dose was calculated according to iodine 131 activity in thyroid and the age-dependent equivalent thyroid dose coefficient. The thyroid equivalent doses assessed in this study were much smaller than the mean thyroid dose in the Chernobyl accident, namely 490 millisievert in evacuees. Compare these data. This is Chernobyl. Here is Fukushima. Also, we carried out biological sampling and analysis. We measured radioactivity of cesium, radiocesium in urine using germanium detector. The maximum effective dose was estimated to be 0.7 millisievert for adults. Our data were published in scientific reports in 2012. Here. Further studies on thyroid dose. Not only radioiodine but also radiocesium in the body were detected in the survey carried out by us in April 2011. So here was the assumption. The ratio between iodine and cesium will be constant when held if these radionuclides in the same plume were taken at the same place. But there would be uncertainties here. When did they inhale? How did they take an action? Additional intake of radiocesium through another pathway by ingestion. Personal difference on biological parameters such as biological half-life and thyroid uptake factor. So we carried out thyroid dose survey for public and we obtained the gamma spectrum like this. Here's a iodine 131 peak. Also, we obtained the peaks of cesium, radiocesium. Then, we determined the counting efficiency of the detector for the calculation of radiocesium activity in the body. We obtain the counting efficiency using a phantom. Then use the ratio between iodine 131 and cesium 134 or cesium 137. It is possible to calculate the thyroid dose using radioiodine activity estimated by whole body counters data. Here is the calibration of measurement equipment under the same geometric arrangement. The radioactive materials were filled with the whole body. That's barium, cesium, and quark. Here is the calculation of the whole body retention due to acute inhalation of cesium 134 on March 15. We measured here after 30 days 0.25.2%. The whole body retention by acute inhalation of cesium. So then date of inhalations here 51.2%. The ratio between iodine 131 and cesium 134 was obtained from 5 persons statistically available among 62 persons inspected as geometric mean of 0.23 and maximum of 0.87. Conservatively, we took the highest value, 0.84. So sodium iodine 131 can be obtained by cesium 134 radioactivity concentration using this value. Here is the result. The maximum value is 18 millisievert. Minimum value is 0.9. The median value is 2.7. It's quite similar to our previous study. Thyroid dose was estimated using whole body counter data obtained from July to August 2011. Only 399 persons whose radiocesium activities were statistically detected among 2,393 persons. In this analysis, additional intake due to ingestion was not considered. For dose restructuring, following information available or needed: time variation, ambient dose rate in cities, activity concentration in environmental or biological samples such as soils, plants, milk, water, and urines. Activity in the body, radioiodine in the thyroid or urine, radiocesium, and the whole body urine. When did radioactive plume pass through cities? Using an air dispersion model, atmospheric activity concentration can be estimated based on the source term analysis. Here are the approaches to initial exposure situations. We have deposition radioactivity just after nuclear accident. If proper air dispersion model is applied, we can obtain the we can estimate atmospheric activity concentrations, but there is a question: how did they deposit on the ground? Dry deposition or wet deposition? Anyway, using the atmospheric activity concentrations, we can get the radiation doses. The ambient dose rate conversion factor for all immersion and ratio of radionuclides, we will have concentration in air. Then, using the conversion factor for internal dose and exposure period, we will get the internal dose. This figure shows a typical time variation of ambient dose rate without wet deposition. This area derived from the dose due to airborne radioactivity. So we try dose estimation using ambient dose rate. Yeah. Dose rate due to air immersion in Iwaki and Fukushima respectively were measured in 1 week after the accident. Eventually, inhaled was assumed during this period 9 hours, and when a radioactive plume due to the accident was staying. Iodine 131 gives 1.6 millisievert as a committed effective dose. Therium equivalent to iodine 132 gave 0.1 millisievert. Most contributable fraction is coming from iodine 131. This is also using a soil activity. We calculated the dose. The iodine 131 was the highest. The conclusion: radioactive plumes enhanced radiation levels in several cities. Therium 132 and its progeny iodine 132 was regarded as one of the most dominant radionuclides, enhanced radiation levels under an initial situation. Thyroid dose due to iodine 132 was estimated to be approximately plus 10%. Thyroid doses of radioiodine 131 were estimated to be 20 to 30 millisievert as a maximum value based on our own data. For restructuring the initial dose, every effort is still being made using environmental radiation data, air dispersion modeling, and deposited radioactivity. This is all my talk. Thank you very much for your kind attention.
Thank you very much, sir. So, dear participants, if you have any question, please unmute yourself and you may ask the question.
The participants are also requested that if they have any queries regarding this course or content, regarding any content which has been delivered by either of the speakers, so you could always send us an email also. So now, formally, let me thank Dr. Shinji Tokunami and for giving his very valuable insights. It is indeed a great honor and privilege to stand here today to express my heartfelt gratitude to Dr. Tokunami for his invaluable contributions in this GIAN course on environmental radioactivity. So, Dr. Tokunami, I think your lectures have been nothing short of enlightening the people, or especially the persons who are working as a researcher in the field of environmental radioactivity. And your deep expertise in the environmental radioactivity, your innovative approaches to the research, and your ability to distill complex concepts into clear and comprehensible ideas have inspired us during the tenure of these 4 days and enriched all of us. I also am very thankful to your commitment to advancing knowledge to this critical area of study, so which is really admirable. So though you are engaging different sessions with your busy schedule, so I thank you that you have spared a lot of time for us and delivered your insight and expertise to make the participants understand that what is the basic things which are required to start a basic research in the field of environmental radioactivity, and what are the different things which they should consider for the measurement, especially like today you have mentioned the different activities which Hirosaki University is undergoing, and a lot of efforts which your university and you are putting. So the knowledge and the perspectives you have imparted will surely guide us in our academic pursuit and research endeavors, and of course the practical applications in the field of environmental radioactivity. So I, on behalf of everyone present here, extend my deepest gratitude on the behalf of my institute, on the behalf of my director, on the behalf of Coordinator GIAN, National Coordinator GIAN, to you, so that you have been an integral part of this program. So as we conclude this session, we hope that the connections formed and the knowledge shared will pave the way for the future collaborations and advancements in this critical issue. So I thank you again, and we wish you continued success in all your future endeavors, and look forward for welcoming you in person in near future. So thank you, sir. So nice of you. And I will be sharing some documents with you, which as your feedback we will be requiring for this program. So today is the last session, but tomorrow is the last session for this GIAN program, where we will be giving some test also, some live demo also, and one basic lecture. So thank you, Dr. Tokunami. Thanks for your time. Thanks once again. Jai Hind, India.
Thank you very much. Thank you very much for kind words. So I'm happy to deliver some lectures. Actually, I spent a lot of time to prepare the many slides. But anyway, so I was happy to be here, and hopefully
in future we will have some physical presence also, and maybe some near
yes,
program.
hopefully.
Yeah.
I will visit India again.
Yeah.
Thank you very much.
Thank you.
So have a nice day. Bye. Thank you.
So thank you very much, sir. So once again, on the behalf of NIT Chandra and Professor Rohit Mehra, sir, I extend my heartfelt thanks to Professor Shinji Tokonami for his valuable time and effort in making this GIAN course a success. So with this, I conclude this last session of the day 4. And again, a reminder for the participants that there will be a lecture tomorrow at 10 a.m. and after that there will be a demonstration session, and followed by that there will be a quiz on the basis of which certificates will be awarded to all the participants. So make sure that everyone is present and to run the quiz. So,
okay, sir. Thank you.
Thank you very much, sir.
Thank you. Goodbye.